Hi, wouldn't it be convenient if you could turn the lights on and off with a TV remote control? Well, you can. All you need is an ATtiny microcontroller. Alright, check it out. On my TV remote control, I've got these four different colored buttons that I don't even know what they're for. A red, a green, a yellow, and a blue one. Well, the blue one I'm going to use to turn the light switch on and off. All the other buttons I can push, change the channels as much as I want, and they're not going to turn the light on. But see, when I push the blue button, the light toggles on. Push it again, it toggles back off. Pretty neat, huh? To see what components I've used here, let's take a look at the schematic. The heart of this device is an Atmel ATtiny13a microcontroller. Also an infrared receiver diode, the part number is VS1838B. Then a couple of AAA batteries and an LED, but the LED you can easily replace with a relay switch. How does this thing work? How does it know which button is which? The format that most manufacturers are using is called the NEC infrared protocol. Here's what that signal looks like, only on my remote control it's actually upside down. It's basically 4 bytes of data, but only one of those 4 bytes really matters, byte number 3. And here you can see that message in the serial COM port monitor of Atmel Studio. Byte number 4 is the binary inverse of byte number 3, so when I push the blue button on the remote control, the value that gets transmitted is hex 61, but the binary inverse of that is hex 79, and the ASCII character that corresponds to this value is lower cap y. There are Arduino libraries that will let you decipher the NEC protocol easily, but I wanted to challenge myself and do it in assembly code for ATtiny13a. Now, of course, it was easier to do this first on Atmel ATmega328p, which is the microcontroller found in Arduino Uno, just because it has UART serial communication capability, which can provide valuable feedback for debugging. Okay, let's go over the code in Atmel Studio 7. It's a good practice to keep register R1 always set to 0. The built-in LED for Arduino Uno is located at pin 5 port B. Please refer back to the Arduino Uno schematic. I need one input on PB0 and one output on PB5. I'm not going to go into the details of setting up the serial communication facility, just use the boilerplate code shown here. The timer I've set up for normal operation with prescaling by the factor of 1024, which at 16 MHz should give us the sampling frequency of 15.6 kHz or the period of 64 microseconds. To initialize the program, I read the status of port B, then I isolate the value on pin 0 and I reset the counter. From here on, I'll keep polling the status of port B in a consecutive manner. Every time the voltage on pin 0 changes from low to high or from high to low, I will call the toggle routine. I will only consider the pulses of high voltage because those are the ones that change in length. For those pulses, I will read the counter to get the length of the pulse. If the length of the pulse is between 15 and 19 counter cycles, I will assign the binary value of 0 to that bit. I will also use the ASCII character 0 to display that value in the serial monitor. Register UDR0 is used to display the result in the serial monitor. I will run all 32 bits of the message to register R21, but after I've shifted all the bits over to the left, only the value of byte number 4 will remain in the register. Then I will reset the counter. If the length of the pulse turns out to be between 32 and 37 cycles of the counter, then I will assign the binary value of 1 to that bit. As before, I will use the ASCII character 1 to display the result in the serial monitor. The value of byte number 4, which is the last byte of the protocol message, will wind up in register R21. This value is the binary inverse of the actual value in byte number 3. And again, we'll reset the counter. When the length of the pulse becomes longer than 38 counter cycles, we can infer that the transmission of the protocol message is finished. In the serial monitor, we will display the ASCII representation of the value in byte number 4. The blue button on the remote control is associated with the value of hex 61, but the inverse of that is hex 79, which corresponds to lowercase y character in ASCII. If the resulting value in register R21 is equal to hex 79, we'll toggle the built-in LED. Command pin is used to toggle the voltage on an output pin of a port. Then we'll reset the counter and we'll continue pulling new samples from port B. So once again we can see that if I push the blue button on the remote control, the result that we'll get in the Atmel Studio serial monitor is a small ASCII character Y, and on the Arduino Uno board the built-in LED will light up. If I push the blue button again, the light will go off, but if I keep pushing other buttons, nothing will happen. The light will not toggle. To program the ATtiny chip, I use Arduino Uno as the programmer. Here's the wiring schematic. The program that is used to upload code to Atmel microcontrollers is called AVR and it's included with the Arduino IDE. Set the uploading output to verbose and copy the relevant parameters from the Arduino IDE to Atmel Studio. Here I use Ctrl+C on the keyboard to copy the path to AVR from the status window of the Arduino IDE. I use a text editor to adjust the format of the path as necessary. AVR is an executable. Some of these parameters need to be in quotes. On my computer, Arduino Uno is connected to COM port 3. You can see that the chip is ATmega 328p and the baud rate is 115,200. W stands for write to flash. An R would mean read, but in this case we want to write. Again, I hit Ctrl+C on the keyboard to copy. Then I pull up the external tools dialog in Atmel Studio. Here you would click the Add button to create a new programming interface, but I've already done that. And then just go ahead and hit Ctrl+V on the keyboard to paste the path. Same thing with the parameters. Click Apply, then OK. For uploading code to ATtiny13a, the path to AVR is the same as before, whereas the parameters should be set as follows. The COM port number may be different on your computer. I got COM port number 3. In order to use Arduino Uno as the programmer for ATtiny13, you need to perform the following setup. Enter this URL in the additional boards manager field in preferences. This link will give you the ability to install in the boards manager an interface to program ATtiny13 chips. Open the Arduino ISP example sketch. Compile it and upload it to the connected Arduino Uno. In the Tools menu, set the programmer choice to Arduino as ISP. In the board manager, go ahead and install the interface for ATtiny13 chips. I can't seem to fit the entire pull-down menu in the recording window here. Just hang on a sec, please. Now you can see the board menu item for ATtiny13. The power supply for the ATtiny are two AAA batteries for a total of 3 volts. The clock speed is 9.6 MHz. The bootloader needs to be burnt onto the chip at least once the first time the chip is used. Then you should be able to upload sketches to ATtiny13a using the Arduino Uno as the programmer. There are some differences between the Atmel AVR ATtiny13a used on Arduino Uno and the ATtiny13a. Namely, ATtiny obviously doesn't have a built-in LED, and pin 5 of port B is used as the reset pin. The assembly program in Atmel Studio needs to be tweaked slightly in order to run on an ATtiny chip. Instead of pin 5, we will use pin 4 of port B for output. Clock frequency of ATtiny is lower, it's 9.6 MHz, so the prescaled sampling frequency will also be lower. It'll be 9.4 kHz. ATtiny does not have UART capability, so we'll remove all the code that pertains to serial communication. Now, because the counter frequency has changed, the lengths of pulses expressed in cycles will also change. Pulses of 9 to 11 cycles in length will be assigned the value of binaryZero, and pulses of 19 to 23 cycles in length will be assigned the binary value of 1. As I mentioned, we'll remove the serial monitoring facilities altogether. Everything else should stay pretty much the same. So one more time, let's take a look at our little infrared receiver in action. Okay, thanks.